So today we are going to be talking about neural network imbalances. And in order to know about the imbalances present in neural networks, we should probably know what a neural network is. Specifically, we're going to be talking about neural network classifiers. So classifiers go ahead and simply put things into classes. These are classes that we define, and ideally, you need a lot of training data that is labeled towards these classes. So you could go ahead and have different type of vegetables, different types of trees, different types of dogs, different visual cues for areas of the world. Whatever sort of categories you wish to go ahead and make are ones that you could make. Now, these neural networks are based upon having large amounts of input to train with, and each piece of training data is going to be what's called the same shape. So it's going to be a array of floating point numbers. Most of the time it's set between 0 and 1, though there are some exceptions where you can have neural networks that have wider ranges, but it's going to be some sort of large array of numbers. So if you had a set of pictures, you're going to have to find some way of transforming those pictures into a large array of floating point numbers. So all of these input nodes or neurons are then attached to a hidden layer. And these different links are going to have what's called activation values. So if the this particular input uh, is of the required activation value for the various hidden nodes it's attached to, it'll go ahead and activate those hidden nodes. Now, for each layer of hidden nodes, it can then be um, attached to either another hidden layer or the output layer. You can feasibly have a unlimited number of hidden nodes, hidden layers, and each layer can have a unlimited number of hidden nodes. Now, these go ahead and filter through and eventually to the output layer, which the output layer is going to have a number of nodes or neurons equal to the number of categories. And these outputs are going to go ahead and get percentages. So this is going to be percentage certainty that it is this particular category. So moving on, the technology that we're going to use is going to be TensorFlow. TensorFlow is open source. It's made by Google. It has several API for Python, JavaScript, C++, and Java, but everyone uses Python, and Python is really the only first class language for this framework. I've tried using it with Java for development, and the documentation is not good. And unless massive changes have been made, I would not recommend using anything other than Python. All right. So the data that's going to be used is the MIS dataset, which is 6,000 handwritten digits, ranging from 0 to 9. They're all labeled. They're black and white, and they're 28 by 28 pixels. In the particular data set in Python, they are NumPy arrays, which are very similar to arrays, but have a lot of mathematical array-based logic built into them. Though, depending upon what you're doing, you might have to shift them back into normal arrays for certain operations, and then shift them back into NumPy arrays. But TensorFlow, for the most part, really requires you to use NumPy arrays for both the input, and what you get out is also a NumPy array. So the model that we're going to make is going to have one activation layer, which this is going to be 28 by 28 times 28 actual input. This flatten thing here is going to go ahead and take that 28 by 28 2D array and reshape it into a 1D array for our input. So it's very easy to input that data. Then we're going to have two hidden layers that are going to be 128 nodes slash neurons each, and they are going to use a ReLU activation function. And our output is going to have 10 categories, 0 through 9, since these are going to be digits. And this layer, the output layer, is going to go ahead and use a softmax function. So softmax goes ahead and just guarantees numbers are between 0 and 1. This is primarily used for the output layer to guarantee that the probabilities um, go ahead and sum to 1. And then the one used on the hidden layers, the ReLU, this one um, just works well with this particular application. There are certainly more analytical methods of determining which activation functions to use with which layers. But there's quite a few, and this talk would quickly diverge into talking about activation functions with a limited time. All right, anyways, so the basic idea. So we want to find imbalance. So in order to find that imbalance, we're going to create a series of masks, 28 times 28 masks, which are going to go ahead and enhance a single index of that 2D array. So it's going to go ahead and increase one part of that array, which is going to be this right here, and then all other parts to go ahead and make sure that we aren't disturbing the data too greatly by adding a huge amount. We're going to slightly decrease all other locations of that array by enough that it will balance out the amount of the increase. So basically, this is just going to enhance one particular section. Then we're going to go ahead and take all of those masks, 28 times 28, and we're going to go ahead and apply it to each piece of training data. So that's going to go ahead and give us an enormous amount of data. And we are going to go ahead and test each one of these masks to see how much change this makes for going towards or away from the target, so we can go ahead and rank how much this mask either enhances the particular data towards the label that it should be, or how much it decreases that. So for the digit 7, if we go ahead and create a histogram, we can see that this histogram is bimodal and it has a left tail. So I interpret this bimodal distribution as the mask that we applied is probably a function of this information here, and probably also helps to generate the tail. Most likely this information is probably normally distributed, but if we go ahead and look at the data, for the 7 digit, we go ahead and at the most extreme, um, so the pixel 12, uh, like x coordinate 12, y coordinate 15, it like will decrease by enhancing that particular pixel. We have decreased its reading on the model to be correctly identified as a 7. On the other side, 27 by 10, that one increased the accuracy by 1%. So the number 7, we have a lot of instances of things that of mask that we could apply that will decrease the correct identification of 7. On the other end, we've got 9. So we this one is also bimodal, long tail to the right. So this one, it just so happens that we have a number of mask and actually fairly extreme outliers that'll go ahead and produce like things that will enhance the amount of nineness with this mask. So particularly 17 by 17 x and like 4y will enhance the model by 24%. So this is quite a substantial increase. Right? So if we go ahead and apply this, so if we go ahead and take the the top well the bottom 16 for the 7 grouping and the top 16 for the 9 model. So the bottom 7 are the ones that decrease the amount of 7ness uh, that the predictive model will make. And the top of the 9 model will increase the amount of 9ness. So with the original reading, we originally started with 99.9% certainty that this is a 7 with the model. Now, if we go ahead and apply this, we get this image, which suddenly we're only 39% certain that this is a 7 and 60% certain that this is a 9. So we have forced a misclassification. Now, we can certainly go further and increase the number of like things that we take from the 9 array, which consist of basically stuff on this side to go ahead and enhance the 9ness, or we can go ahead and take from the 7 array on the low end to decrease the 7ness. But for this to be effective, we probably want to use as little as possible because this already, like to the human eye, looks to have some amount of distortion. I would assume most humans would just read this clearly as a 7 that just had some ink blot on it. But if we are dealing with data that is in a, say, higher number of dimensions where humans can't necessarily easily interpret the information, this sort of distortion can be much harder to identify. But a way that we might defend against this is go ahead and take all of these masks, apply it to all of our training data, and then go ahead and retrain based upon that training data. So if we go ahead and do that, that goes ahead and results with proper classification of the 7 and proper classification of this 7 as well. We went ahead and went from a 100% to 100% with very little certainty that this was a 7. But with going ahead and applying all these masks, we have accidentally overtrained our model. Right now, it is very certain uh, on the training data, but if we were to give it very novel and unique data that um, is like set like numeric digits, but dissimilar from the digits that are in the training set, it might have a lot of difficulty identifying those. As well, if we just go ahead and increase the amount of things that we take from the things that take away from the sevenness, or increase the number of things that increase the nineness of this thing, we can go ahead and cause a, um, a misclassification. So instead of taking in the previous grouping the bottom 16 and the top 16, we're just going to take the bottom 20 and the top 20. And even with this very overtrained model, we have now caused misclassification. We went from 100% to 48%, and notice we went from 0% on the 9 to 51%, which if we go ahead and just choose whichever is the highest probability, uh, our model has now misclassified this as a 9. So this isn't necessarily a good way of dealing with imbalances. So bias can be kind of hard to detect in these sorts of neural networks. Even when we go ahead and use these sorts of like extra sets of data to try and get rid of that bias, we can overtrain. And as you noticed, we just need to slightly increase the amount that we use to cause that flip. So that doesn't even overtraining doesn't even remove that bias. Uh, and like on other like talks and research papers on the subject, like it's very common for like people to mention like, oh, we just limit the number of queries to the neural network and that solves the problem. No, that only slows it. Like if you go ahead and look at classical problems like heartbleed, which typically requires an enormous amount of sampling, um, the like that particular attack was shown to still be feasible over long periods of time. So if you limit access to your neural network, well, you might be removing the amount of features that this neural network, like that its functionality, by limiting access. But unless you completely remove access, you're not removing the problem, you're just slowing it down. And as well, a classic adage of attacks is that they only become more advanced. This is a very primitive brute force attack. I'm pretty sure many very advanced researchers are going to go ahead and find far more nuanced and elegant forms of attack that will probably be much harder to detect. Like here, like there is clearly some amount of noise, but this is probably not the ideal measurement of imbalance. That there is probably a more subtle form of imbalance that's present in this neural network that can be detected through other means and then exploited. So these are definitely things to be aware of when you go ahead and generate neural networks that are classifiers, and one should be seeking new and novel ways of trying to mitigate these types of attacks. Well, I hope this was interesting, and I hope everyone learned something.